In this lesson we're going to look at transformers and how they work. So basically a transformer is a device which transfers an electric current and voltage from a primary circuit through to a secondary circuit using a magnetic field which passes through a magnetic core. So let's just label this simple device. So we have the core, which is made from a magnetically soft material such as iron, or soft iron as it's known. And this has the important property that it's able to be magnetized and demagnetized rapidly. So this is the primary coil, that's the primary circuit, and this is the secondary coil. So how does the transformer work? Well, okay, so first of all what we're going to have is a changing input voltage into the primary coil. Now, as you well know from Ohm's law, that the voltage in electric circuit is directly proportional to the current and vice versa. So if you have a changing input voltage in a circuit, then you will also have a changing current. So we get a changing current in this primary coil, and that changing current will produce a changing magnetic field in the iron core of the transformer. Okay, so we're going to get a changing magnetic field in the core of the transformer. What's going to happen then is the changing magnetic field will cut through the secondary coil, and that will induce a changing current in the secondary coil, which again, as before, because the voltage is directly proportional to the current in the circuit, we will also get a changing voltage in the secondary coil. Let's just summarize that again. In the primary coil we've got a changing current and therefore changing voltage, which we'll call IPVP. This produces a changing magnetic field in the core, which will induce a changing current and voltage in the secondary. So just to emphasize this, that the current has to be changing. This induction effect will not work if the magnetic field in the core is fixed, if it's permanent, if it's not changing. So we must have a changing magnetic field in the core. Therefore, we must have a changing electric current and voltage in the primary coil. So for example, in the UK and in most countries across the world, power stations transmit electricity at a frequency of 50 Hz alternating current. So we have a 50 Hz voltage coming into the primary coil. That means also 50 Hz current, which means that the magnetic field inside the core will be changing 50 times a second, 50 Hz. Okay, so you'll be magnetizing and demagnetizing the core 50 times a second. So it's very important here that you have a magnetically soft material. If the magnetic material retains its magnetism in any way, then that's going to cause some of the electrical energy which is coming into the primary coil to be converted to heat in the core, which means that energy is going to be lost. So magnetically soft material is very important for the core. That's going to produce in the secondary coil a 50 Hz AC current and likewise a 50 Hz output voltage. Okay, so let's just think about the transformer equations. That's to say how the input voltage and the output voltage is related to the number of turns in the primary and secondary coils. Okay, so just labeling the transformer again, we've got the primary and secondary coils, and we've got a input voltage Vp into the primary, and the number of turns in the primary coil is Np. Okay, and in the secondary coil we've got an output voltage Vs, voltage secondary, and the number of turns in the secondary coil is given by Ns. Okay, what can we say then? Well, we can say that the ratio between the input and output voltages, that's say Vp and Vs, is equal to the ratio between the number of turns in the primary coil to the secondary coil. Putting that in a slightly more mathematical form, we can say Vp, voltage over the primary, divided by voltage in the secondary, that's the ratio of Vp to Vs, is equal to, again, the ratio of the number of turns of the primary to the number of turns of the secondary. Or, it doesn't matter which way you write this ratio, you can turn it upside down. You could have the voltage in the secondary to the voltage of the primary is equal to the number of turns in the secondary divided by the number of turns in the primary. So it's very typical in the GCSE, IGCSE exam that you need to calculate, for example, one of these factors. You'll be given, for example, this one, and this one, and you'll need to calculate, for example, the number of turns in the secondary. We'll look at examples of transformer problems in a later lesson. That's your transformer equation. Just to finish off with, we need to look at the power considerations with respect to transformers. So looking at power transfer in the transformer, remembering that we've got a soft iron core. That's a magnetically soft material. In fact, these soft iron cores used in transformers are virtually 100% efficient. So no energy is lost to heat in the transformer. Virtually all of the electrical energy going into the transformer is transferred from primary to secondary without loss. So we remember that from the unit on electricity, that the power in an electric circuit is equal to the voltage times the current. Here it's the voltage in the primary times the current in the primary. And the output power will be equal to the voltage in the secondary times the current in the secondary. And so what we can say is that if our transformer is 100% efficient, which we're assuming is the case, then the power in to the transformer must be equal to the power out. So we can say that VP IP is equal to VS IS. Again, you can also expect questions in your GCSE exams based on power transfer in transformers. Again, you'll be given 3 of these bits of information, and you will have to calculate the 4th variable. For example, in this case it would be the voltage in the secondary coil. Okay, just to finish off with, we're going to introduce the concept of a step up or step down transformer. In a step up transformer, the output voltage is larger than the input voltage. In a step down transformer, the output voltage is less than the input voltage. And this all depends upon the number of turns in the coil. Okay, so just going back to our transformer equation, this is actually the second option that we looked at, and just going to quickly rearrange that a minute so we can say that the voltage in the secondary, move this over here now, rearrange the equation, is equal to the voltage in the primary multiplied by the number of turns in the secondary divided by the number of turns in the primary. What that means is the output voltage is going to be greater when the number of turns in the secondary is larger than the number of turns in the primary. So we get a step up transformer. This is a step up transformer because it has more turns in the secondary than in the primary. In the second case here, the number of turns in the secondary, as you see, is less than the number of turns in the primary. So that means that the output voltage is going to be less than the input voltage. So this is going to be a step down transformer. So just visually looking at them, you see step up means more turns in the secondary than the primary. Step down means more turns in the primary than in the secondary. Now, the use of step up and step down transformers is incredibly important in the whole area of the transfer of electrical energy from power stations to your home. Okay, so we're going to look at this whole area of the use of transformers in the following lesson.